Next, I want to talk about a type of truss that is impossible to slice three members. They're very special. They're called K trusses, and it makes me think of the cereal Special K. This is a K truss, and it gets its name because you can see K's in there. See, there's a K's going forward. Here's a backwards K over here. If you're a baseball fan, every time someone strikes out, the fans will put out a K. I think a forward K means striking out swinging, and a backwards K means striking out looking. It's one way or another. But anyway, if you want to find, let's say, the force in one of the legs of the K, there is no way to slice this without cutting 4. So you try that. Nope, that cuts 4. You can try this. That cuts 4. Just believe me, I've tried this several times. It is impossible to cut just 3 members in a K truss. And so what we need to do is find some special way to solve this special K truss. The key to solving K trusses by the method of sections is first using the method of joints and looking at the knee of the K, where the 2 legs come in. Here's the free body diagram of that joint in the K truss. You have the upper member, the lower member, you have one of the knee members there and the other knee member. In this derivation, we're going to assume that these 2 angles are equal. You can apply this concept I'm about to show you for unequal angles, but for simplicity and for this class, we'll just say that the upper angle and lower angle in this K truss are equal. What we're going to do first is look at sum fx equals 0, and we're going to look at it in our little trick using just the x and y components. So that's all in the y. Let's see, we'll have this one going up. Okay, can you see that for the sum of the forces in the x to be 0, this bottom one has to be coming in. And if the angles are the same, this force x component there, A, has to equal this component there, A, because this will have a horizontal component of A going that way, and this one will have a horizontal component of A going this way. So if the angles are equal, these 2 forces here, let's call them F knee, K for knee, because, you know, that thing looks like a knee. Anyway, those have to be equal for the x forces to cancel out if the thetas are the same. If the thetas were different, there'd be a ratio of cosines in there, or sines, or something like that. Well, if the x components are equal, the y components are equal. But the main thing is that these 2 forces are the same. And so now when we take a vertical slice through the K, we are only slicing 3 unknowns, even though we're slicing 4 members. So let's look at a problem and illustrate how this works. Here's our K truss again, all loaded up, and I'm telling you that the angle of the knee is 45 degrees from the verticals. And I want you to find the force in the inclined members of that K. Here's our slice, and even though it cuts through 4 members, it only cuts through 3 unknowns, because remember the force in the 2 angled legs of the K are equal, so that's only 1 unknown. Oops, I forgot to do the first step, get the reaction. So let's just say that's 17.5 kips, and that's 17.5 kips. Okay, next we're going to close the loop. There we go. And we're going to draw the free body diagram. You don't need to watch me draw that thing, so I'm just going to paste it in here. And here's the free body diagram. I've drawn in all the forces, and I'm about to draw in the things I've cut through. I've put the top and bottom forces in tension, but now, before I draw in the forces in the K members, in those inclined members, let's look at the vertical forces. We have a total of 17.5 going up on that reaction, and we have 15 coming down. That means there needs to be another 2.5 going down. Okay, this will be an equilibrium. 17.5 going up, 17.5 coming down. I'm going to move this 2.5 over here on the side just to remind us. Well, remember that in the K, they have to be both one coming in and one coming out for the X components to cancel out, or it could be this way. As long as one is coming in and one is coming out, that'll be an equilibrium because the forces are equal and the angles are equal, so the X components will cancel out. Well, in this case here on the left, the total vertical component is going down, and in this case on the right, the total vertical component is going up. I just said we need 2.5 going down. What that means is that force is going in, this force is coming out. If you look right here at the joint, those will have the X forces cancel out. Remember, they have to do that at the joint. But what they do is they have the Y components both pointing down. And if you remember what we said in this K joint, if the angles are equal, these vertical components are equal. And so if we have a total of 2.5 coming down, that means that this component there has to be 1.25, half of it, and that component has to be 1.25, half of it. And finally, because we know the angle is 45 degrees, that's 1.25, that's 1.25, and by Pythagorean theorem, we get the force is square root 1.25 squared plus 1.25 squared square root, and that comes out to 1.77 kips. So again, the strategy is you make a slice, you get the net vertical force in the two legs, and half of that is in each leg, and then you use the geometry to get the total force. Okay, we cannot talk about ninjas and trusses without talking about Nijo Castle in Kyoto. In the U.S., we design floors to not squeak, and when a floor squeaks, what's happening is that the flooring that's nailed to the joists under it, it's squeaking because the nails are moving up and down, and you're hearing the nails slide in and out of the wood, and it squeaks. And we solved that problem in the U.S. by putting joists every 16 inches or so the nails can't move in or out, because we don't want our floors to squeak. Well, if you go to Nijo Castle in Kyoto, and they have this hallway here, and it's called the Ugui Subari floor, or the Nightingale floor. And when you walk on this floor, it squeaks. It goes eek, eek, eek. And if you look underneath it, it has these special things here under the floor to squeak on purpose. They purposely make this floor squeak. And the reason is that a royal family lived in here, and they're constantly being targeted for assassination. And so it's a warning system. When you walk in there, when they send the ninjas in there to kill them, the floors squeak, and the guards can come out and save them. But there's one fatal flaw in this strategy, is that I've seen movies and ninjas can crawl on the roof upside down. But anyway, that's Nijo Castle in Kyoto.